What is a galaxy? The Milky Way galaxy. Which galaxy do we live in? Look up at the night sky. At first it seems calm, silent, almost empty. But that darkness is an illusion. Behind the veil of night lies a vast, moving architecture of matter and energy, an ancient structure built over billions of years. What you see as tiny points of light are not just stars. They are signposts, markers of something far larger. They are pieces of galaxies. And one of those galaxies is our home. The meaning of a galaxy. A galaxy is not just a collection of stars. It is a cosmic city, a gravitationally bound system made of hundreds of billions of stars, surrounded by planets, moons, nebula, clouds of gas and dust, dark matter, and, at its heart, often something far stranger. Galaxies are the largest organized structures in the universe, held together by gravity. They are ancient. They are dynamic. They are alive with motion. Every galaxy is a story, written in light, gravity, and time. How galaxies came to exist. In the beginning, there were no galaxies. After the Big Bang, the universe was hot, dense, and nearly uniform. Matter existed, but it was scattered. There were no stars, no planets, no light as we know it. Only darkness and potential. As the universe expanded and cooled, tiny irregularities, slight differences in density, began to grow. Gravity pulled matter inward. Clouds of hydrogen and helium collapsed. The first stars ignited. These stars gathered into clusters. Clusters merged into larger structures. And over hundreds of millions of years, the first galaxies were born. Galaxies did not appear suddenly. They assembled slowly and violently, shaped by gravity and time. Different types of galaxies. Not all galaxies are the same. Some are elegant and orderly, others are chaotic and wild. Astronomers classify galaxies into several main types. Spiral galaxies, with graceful arms winding outward from a central core. Elliptical galaxies, massive and smooth, shaped like glowing spheres or stretched ovals. Irregular galaxies, distorted and uneven, often shaped by collisions or gravitational encounters. Each type tells a different evolutionary story. And our home belongs to one of the most visually striking kinds. The Milky Way galaxy. We live inside a spiral galaxy known as the Milky Way. Its name comes from ancient observers who saw a faint, milky band stretching across the night sky, a soft river of light. They did not know what it was, but they were looking directly into the heart of our galaxy. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure of stars, with spiral arms extending outward. It is vast beyond everyday comprehension. Approximately 100,000 light-years across, containing an estimated 100 to 400 billion stars, and possibly trillions of planets. This galaxy is not static. It is rotating. Our entire galactic disk turns slowly, completing one full rotation roughly every 225 to 250 million years. This is called a galactic year. The last time the Sun completed one full orbit around the Milky Way, dinosaurs still ruled the Earth. Where are we inside the Milky Way? We are not at the center. We are not near the edge. We live in a quiet suburb of the galaxy. Our solar system is located in a minor spiral arm called the Orion Arm, also known as the Orion Spur. It lies between two major arms, the Sagittarius Arm and the Perseus Arm. From here, we orbit the galactic center at a speed of about 220 kilometers per second. Yet we feel nothing, because everything around us is moving too. The galactic center. At the heart of the Milky Way lies something extraordinary, a supermassive black hole. Known as Sagittarius. A star, it contains the mass of about 4 million suns, compressed into a region smaller than our solar system. It does not roam the galaxy. It anchors it. Stars near the center orbit at incredible speeds, pulled by its immense gravity. Gas clouds swirl, radiation bursts outward. Yet from our distant location, the galactic center is hidden, obscured by thick clouds of dust and gas. We cannot see it with our eyes, only with instruments tuned to radio waves, infrared light, and X-rays. The spiral arms. The Milky Way's spiral arms are not solid structures. They are regions of higher density, where gas and dust are compressed as the galaxy rotates. These regions trigger star formation. This is why spiral arms glow with bright, young blue stars, hot, massive, and short-lived. Our Sun, however, is middle-aged. It formed about 4.6 billion years ago, long after the Milky Way itself took shape. We are passengers in an ancient structure, riding a spiral arm through cosmic time. What the Milky Way is made of stars make up only a small fraction of the galaxy's mass. Most of it is invisible. The Milky Way is embedded in a vast halo of dark matter, a mysterious substance that does not emit light, but exerts gravity. As we try to understand the Milky Way, it becomes clear that our galaxy is not simply a backdrop for life, but an active system shaped by constant change. Stars are born, evolve, and die within it. Gas clouds collapse under gravity, igniting nuclear fusion. Massive stars explode as supernovae, enriching the surrounding space with heavier elements. These elements later become part of new stars, planets, and eventually living organisms. In this way, the Milky Way continuously recycles matter, turning the remnants of dead stars into the building blocks of new worlds. Our position inside the galaxy limits what we can see. Unlike distant galaxies, which we can observe as complete shapes, the Milky Way surrounds us. Dust clouds block visible light, hiding large portions of the galactic disk and the central region. For centuries, humans could only guess at the galaxy's true structure. It was only with the development of radio astronomy, infrared telescopes, and space-based observatories that scientists began to map the Milky Way more accurately. Even today, many details remain uncertain, and our picture of the galaxy is still incomplete. One of the most important discoveries about the Milky Way is that it is much larger and more massive than what we can directly observe. The visible stars and gas account for only a small fraction of its total mass. Measurements of stellar motion show that stars far from the center move faster than expected, indicating the presence of unseen matter. This led to the conclusion that the Milky Way is embedded in a massive halo of dark matter. This invisible component extends far beyond the visible disk and plays a crucial role in holding the galaxy together. The Milky Way's history is also marked by collisions and mergers. Over billions of years, our galaxy has absorbed smaller dwarf galaxies, stretching their stars into long streams that still orbit within the galactic halo. These stellar streams are fossil records of past encounters, allowing astronomers to reconstruct the Milky Way's growth over time. Our galaxy did not form in isolation. It grew by interaction, shaped by gravity and cosmic evolution. Star formation within the Milky Way is not evenly distributed. Most new stars form in the spiral arms, where dense clouds of gas are compressed by galactic rotation. These regions are filled with bright, short-lived stars and glowing nebulae. In contrast, the central bulge contains older stars and less gas, while the outer regions of the galaxy are quieter and more sparsely populated. This uneven distribution tells us that the Milky Way is still evolving, still changing its internal structure. From a broader perspective, our galaxy is just one member of a much larger cosmic network. The local group itself is part of an even greater structure called the Virgo supercluster, which contains thousands of galaxies bound together by gravity. On the largest scales, galaxies form filaments and walls separated by vast cosmic voids. The Milky Way occupies a small position within this immense cosmic web, emphasizing how limited our local viewpoint truly is. Understanding which galaxy we live in is more than a question of location. It is a question of context. The Milky Way defines the environment in which our solar system formed, the materials available to build planets, and the conditions that allowed life to arise on Earth. If our galaxy were very different, more violent, poorer in heavy elements, or lacking stable regions, life as we know it might never have emerged. Yet even with all we have learned, the Milky Way remains partly unknown. We do not fully understand how its spiral structure is maintained, how dark matter is distributed within it, or how its central black hole influences the rest of the galaxy. Each new observation answers some questions while raising others, reminding us that knowledge of our galactic home is still evolving. And this leads to a larger realization. If our own galaxy, the one we inhabit, still holds so many mysteries, then what about the countless other galaxies scattered across the universe? What differences exist between them? How do their histories compare to ours? And what can they tell us about the origin, structure, and ultimate fate of the cosmos itself? To truly understand the Milky Way, we must place it among other galaxies, compare it, and explore what lies beyond its boundaries. Only then can we begin to grasp whether our galactic home is ordinary or something rare in the vast universe. And this is where the journey must continue. As astronomers continue to study the Milky Way, they have come to realize that our galaxy is not a simple uniform system. Instead, it is made up of multiple overlapping components, each with its own structure, age, and role in the galaxy's evolution. These components include the galactic disk, the central bulge, the stellar halo, and the dark matter halo. Together, they form a complex gravitational system that has been shaped over billions of years by internal processes and external interactions. The galactic disk is the most visually prominent part of the Milky Way. It contains most of the galaxy's stars, gas, and dust, and is the region where spiral arms are found. This disk is relatively thin compared to its width, extending about 100,000 light-years across, but only a few thousand light-years thick. Within the disk, stars orbit the galactic center in roughly circular paths. The disk is also where most star formation occurs, as it contains large amounts of cold gas capable of collapsing into new stars. Our solar system lies within this disk, making it the region of the galaxy we understand best. At the center of the Milky Way lies the galactic bulge, a dense, roughly spherical region packed with older stars. These stars tend to be much older than those found in the spiral arms, indicating that the bulge formed early in the galaxy's history. The bulge also contains the supermassive black hole Sagittarius A star, whose gravitational influence dominates the central region. Although this black hole is relatively quiet compared to those in some other galaxies, its presence has likely played an important role in shaping the Milky Way's evolution. Surrounding the disk and bulge is the stellar halo, a diffuse and sparsely populated region containing some of the oldest stars in the galaxy. These stars move in highly elliptical orbits that take them far above and below the galactic plane. Many of them are remnants of smaller galaxies that were absorbed by the Milky Way long ago. By studying the chemical composition and motion of halo stars, astronomers can trace the galaxy's past mergers and reconstruct its formation history. Beyond the visible components lies the dark matter halo, which extends far beyond the region occupied by stars. Although dark matter cannot be observed directly, its presence is inferred through its gravitational effects. The rotation curves of the Milky Way show that stars and gas orbit the galaxy faster than they should if only visible matter were present. This discrepancy can only be explained by the existence of a massive, unseen halo of dark matter. Without it, the Milky Way would not be gravitationally stable. The study of the Milky Way is complicated by our location within it. Unlike distant galaxies, which can be observed as complete systems, our galaxy must be mapped from the inside. Dust obscures large regions of the disk, especially toward the galactic center. As a result, astronomers rely on multiple wavelengths of light to peer through these dusty regions. Radio waves reveal cold gas clouds, infrared light penetrates dust to show hidden stars, and X-rays expose high-energy processes near the galactic center. Each wavelength provides a different piece of the puzzle. Advances in space-based observatories have dramatically improved our understanding of the Milky Way. Missions such as Gaia have measured the positions, distances, and motions of billions of stars with unprecedented precision. This data allows astronomers to construct detailed three-dimensional maps of the galaxy and study how stars move within it. These measurements reveal subtle patterns in stellar motion that reflect the Milky Way's gravitational structure and past interactions. One of the key insights from these observations is that the Milky Way is not in perfect equilibrium. Its disk shows ripples and asymmetries, likely caused by interactions with nearby dwarf galaxies. The Sagittarius dwarf galaxy, for example, is currently being torn apart as it passes through the Milky Way, leaving behind streams of stars that wrap around the galaxy. These ongoing interactions demonstrate that galactic evolution is an active process, continuing even in the present day. Star formation within the Milky Way follows a complex cycle. Giant molecular clouds, composed primarily of hydrogen, serve as stellar nurseries. Within these clouds, regions of higher density collapse under gravity, forming protostars. As these protostars grow hotter and denser, nuclear fusion ignites in their cores, marking the birth of new stars. Over time, stellar winds and radiation from young stars disperse the surrounding gas, ending the period of star formation in that region. This cycle repeats across the galaxy, shaping its appearance and evolution. Massive stars play a particularly important role despite their short lifespans. When they explode as supernovae, they release enormous amounts of energy and heavy elements into the surrounding space. These explosions trigger new waves of star formation while enriching the interstellar medium with elements such as carbon, oxygen, and iron. Without this process, rocky planets and life itself would not be possible. In this sense, the Milky Way functions as a vast chemical factory, continuously producing and redistributing the elements necessary for complex structures. The Sun is a relatively ordinary star in an ordinary location within the Milky Way. It is not especially massive, nor does it reside near the galactic center or in a particularly active star-forming region. This relative calm may be one reason life was able to develop on Earth. Regions closer to the galactic center experience higher radiation levels and more frequent supernovae, which could pose challenges for the long-term stability of life. Our position, far from the center but still within the disk, appears to be a relatively safe and stable environment. This idea has led scientists to propose the concept of a galactic habitable zone. According to this hypothesis, certain regions of a galaxy may be more favorable for life than others. These regions must contain enough heavy elements to form rocky planets, while avoiding excessive radiation and gravitational disturbances. While this concept is still debated, it highlights the importance of galactic-scale conditions in shaping the potential for life. The Milky Way's future is shaped by both internal processes and external influences. Over time, star formation will gradually decline as the galaxy's gas supply is depleted or heated. Meanwhile, interactions with neighboring galaxies will continue to reshape its structure. The eventual collision with the Andromeda Galaxy will dramatically alter both systems, leading to the formation of a new, larger galaxy. This event will mark the end of the Milky Way as we know it, though the stars themselves will largely survive the transition. Despite its immense size, the Milky Way represents only a tiny fraction of the observable universe. Modern telescopes have revealed that galaxies are ubiquitous, filling the cosmos in vast numbers. Some are smaller and simpler than our own, while others are far larger and more massive. By comparing the Milky Way to these other galaxies, astronomers hope to understand which of its features are common and which are unusual. These comparisons raise fundamental questions. Is the Milky Way a typical spiral galaxy, or does it occupy a special niche? Are its relatively calm history and stable structure common among galaxies of its size? Or are these conditions rare, making our galactic home unusual in some important way? Answering these questions requires looking beyond our galaxy and studying the broader population of galaxies across cosmic time. As we push our observations deeper into space, we are also looking further back in time. Distant galaxies appear as they were billions of years ago, offering a glimpse into earlier stages of galactic evolution. By studying these ancient systems, astronomers can piece together how galaxies like the Milky Way formed and changed over time. Each observation adds to a growing narrative that connects the early universe to the present day. Ultimately, understanding which galaxy we live in is only the first step. The Milky Way is a single example within a vast cosmic ecosystem. Its structure, history, and future are intertwined with those of countless other galaxies. To truly understand our place in the universe, we must continue outward, exploring how galaxies interact, evolve, and shape the cosmos on the largest scales. And as this exploration continues, new questions emerge. What lies beyond the local group? How do galaxies cluster into superclusters and filaments? What role does dark energy play in shaping the large-scale structure of the universe? These questions lead us away from our galactic home and toward the broader architecture of the cosmos itself. This is where the next chapter begins. As we expand our view beyond the Milky Way, it becomes clear that galaxies do not exist in isolation. Gravity binds them into larger systems, creating a hierarchy of structure that extends far beyond any single galaxy. The Milky Way belongs to the local group, a gravitationally bound collection of galaxies spread across several million light-years. Within this group, galaxies interact subtly and sometimes dramatically, exchanging material, distorting one another's shapes, and influencing each other's long-term evolution. The local group is dominated by two large spiral galaxies, the Milky Way and the Andromeda Galaxy. These two giants account for most of the group's mass and gravitational influence. Surrounding them are dozens of smaller dwarf galaxies, many of which orbit the larger systems. Some of these dwarfs are actively forming stars, while others are composed mostly of old stars and little gas, suggesting that their star-forming days are largely over. These small galaxies are important because they represent the building blocks from which larger galaxies formed. Galactic interactions within the local group occur over immense timescales. Although galaxies move at hundreds of kilometers per second, the distances between them are so vast that encounters unfold over billions of years. When galaxies pass close to one another, tidal forces stretch and distort their structures. Gas clouds can be stripped away, star formation can be triggered or suppressed, and long streams of stars can be pulled into intergalactic space. These processes gradually reshape galaxies, leaving behind signatures that astronomers can detect long after the interactions have occurred. Beyond the local group lies an even larger structure, the Virgo supercluster. This immense collection of galaxy groups and clusters spans more than 100 million light-years. The Milky Way occupies a relatively quiet region within this supercluster, far from its dense core. On even larger scales, superclusters themselves form part of an intricate cosmic web. Galaxies trace vast filaments that stretch across the universe, intersecting at dense nodes and surrounding enormous voids where few galaxies exist. This large-scale structure did not arise randomly. It reflects the initial conditions of the early universe, shaped by tiny fluctuations in density that were amplified by gravity over billions of years. Dark matter played a central role in this process, forming the gravitational scaffolding upon which galaxies assembled. Ordinary matter fell into these dark matter structures, cooling and condensing to form stars and galaxies. In this sense, the Milky Way is not just a collection of stars, but a visible expression of much deeper cosmic processes. Studying the Milky Way within this broader context helps astronomers understand its past and predict its future. For example, the galaxy's relatively thin disk suggests a history with fewer major collisions compared to some other galaxies. Large mergers tend to thicken galactic disks or destroy them entirely, transforming spiral galaxies into elliptical ones. The fact that the Milky Way remains a well-defined spiral implies that it has experienced a comparatively calm recent history, with no major mergers in the last several billion years. However, this calm is not permanent. The ongoing interaction with the Andromeda Galaxy will eventually dominate the Milky Way's future. As the two galaxies approach each other, their mutual gravitational attraction will distort their shapes, triggering waves of star formation and redistributing gas and stars. Over time, repeated close passes will lead to a full merger, resulting in a single, more massive galaxy. This future system will likely lack the familiar spiral structure we see today, marking a profound transformation in our galactic environment. Despite these dramatic future changes, the timescales involved are so long that they exceed the expected lifespan of the Sun. Long before the Milky Way and Andromeda merge, the Sun will exhaust its nuclear fuel and evolve into a red giant, eventually shedding its outer layers and leaving behind a white dwarf. From a human perspective, these events are unimaginably distant, but from a cosmic perspective, they are part of an ongoing and continuous process. Understanding our galaxy also requires understanding the role of time in astronomy. When we observe distant objects, we see them as they were in the past. Light from the center of the Milky Way takes tens of thousands of years to reach us, meaning that even our view of our own galaxy is a glimpse into history. When we observe distant galaxies billions of light years away, we are seeing them as they existed when the universe was young. By comparing these observations, astronomers can trace how galaxies evolve over cosmic time. This ability to look back in time reveals that galaxies like the Milky Way were once smaller, more chaotic systems. Early galaxies were rich in gas and formed stars at much higher rates than we observe today. Over time, star formation slowed as gas was consumed or expelled. The Milky Way represents a mature stage of galactic evolution, still active but far less intense than in its early history. This gradual transformation reflects a balance between gravity, star formation, and feedback from stars and black holes. The question of how typical the Milky Way is remains an open one. While spiral galaxies are common, not all spirals share the same properties. Some have much larger central bulges, others have weaker or stronger spiral arms, and some host extremely active central black holes. By comparing the Milky Way to a wide range of galaxies, astronomers aim to identify which of its features are common outcomes of galactic evolution and which may be the result of unique circumstances. This comparison also informs the search for life beyond Earth. The characteristics of a galaxy influence the types of stars and planets that form within it. Galaxies with intense star formation and frequent supernovae may be hostile environments for life, while quieter galaxies may offer more stable conditions. Understanding where the Milky Way falls within this spectrum helps scientists evaluate how common life-supporting environments might be in the universe. As observational technology continues to advance, new questions continue to emerge. Upcoming telescopes and missions will probe the Milky Way in greater detail than ever before, mapping its structure, tracing its motion, and revealing faint objects that were previously invisible. At the same time, surveys of distant galaxies will expand our understanding of how galaxies form and evolve across cosmic history. Each new discovery adds depth to our understanding, but also reveals the limits of our knowledge. The Milky Way, despite being our home, still holds many mysteries. Its exact mass, the detailed distribution of dark matter, the long-term behavior of its spiral arms, and the influence of its central black hole are all areas of active research. These unknowns remind us that astronomy is not a finished story, but an ongoing investigation. And as we continue to explore these questions, it becomes clear that learning about the Milky Way is not just about understanding one galaxy. It is about understanding how structure emerges in the universe, how matter organizes itself on the largest scales, and how environments capable of supporting life come into being. From here, the next step is unavoidable. To fully appreciate the significance of our galaxy, we must look outward and examine galaxies far beyond the local group. Only by comparing our galactic home to the vast diversity of galaxies across the universe can we begin to understand its true place in the cosmic story. That exploration leads us beyond familiar territory, toward distant galaxies, ancient light, and the early universe itself. And it is from this single quiet corner of the Milky Way that humanity will continue to look outward, seeking to understand not only where we live, but why the universe took this particular shape around us.